how do we put all this together? Why are we talking about this? Well, check it out. There are different kinds of atoms, and we call those elements, right? And it's one property of the atom that determines what element it is, and that's the number of protons, right? The number of protons. And if you look at a periodic table, I should have had a periodic table I can bring up, but I forgot to. But if you look at the periodic table, every element on the periodic table has a little number up in the corner, and that's telling you how many protons that particular element has. So the difference between different elements is just the number of protons in the nucleus, okay? What's the smallest number of protons it can have? 1, right? The smallest number of protons an atom can have is 1. Do any of you happen to know what element is that smallest, simplest type of atom with just 1 proton? Does anybody know what that element is? I'm not requiring you to memorize a bunch of elements or anything. But what's the simplest 1 proton element? That's correct. It's hydrogen. I do want you to know that element, okay? Hydrogen is the smallest element. It has only 1 proton, okay? There's one other element that I want you to remember, and that's the one that has 2 protons. Any of you guys know which one has 2? This is the only other one that you need to know. I'll tell you in a second, but do you guys know? 2 protons. What are we looking at? It's okay. Oh, there you go. Somebody got it. It's helium. Helium. So hydrogen has 1 proton. Helium has 2. Every other element has more and more protons, right? More and more depending on the element, okay? Why do I want you to know those 2 elements, hydrogen and helium? It's because hydrogen and helium are by far the most common elements in the universe. If we look out in space, hydrogen and helium are much more common than every other element. Every other element is actually pretty rare. So carbon, that's all over our body, rare. Oxygen that we're breathing, rare. Gold, obviously rare, right? But hydrogen and helium are very common, okay? How common am I talking? Well, let me put it this way. 75% of all matter out there is hydrogen, okay? 75% of the elements out there is hydrogen, okay? Close to 25% is helium, all right? 75% hydrogen, close to 25% helium. Let's do a little bit of math. Let's do a little bit of math here. If we take that 75% hydrogen and that close to 25% helium, what percent are we at? What percent are we at now? If we add those together, what percent do we have? 75% hydrogen plus about 25% helium. What do we get? Oh, come on, guys. You can do that math. All right. Fine. It's 100%. It's 100%. It's close to 100%, right? If you take 75 plus about 25, you get about 100, right? So that means that almost 100% of all of the elements in the universe are hydrogen and helium, and everything else is just a sprinkling. Okay, now, here we go. Let's get into this. So, we're trying to figure out how can you look at an object and know which elements it's made out of. Can you see, yes or no, can you see when you're just looking look at the table in front of you, can you see the protons? Can you see the protons? Nah, you can't, right? So that means that you can't just count the protons to know what element you're looking at. So what do we do? what do we do? Okay. Another way to think of an atom, or let me kind of draw this real quick. We said it's sort of like a little miniature solar system. So imagine that's the nucleus. I'll put a plus on it because the nucleus is positive. And imagine that we've got electrons orbiting around it on little orbits. Okay. Now, here we go. So this sort of looks like a little solar system, but we already said it's not exactly the same as a solar system because gravity's not important. But that's not the only way that it's not like a little miniature solar system. There's a more important way that it's different from a solar system that we are going to be able to use to put all of this together. And that's this. If this was a solar system, and this was the sun, and these were little planets, then you can have planets orbiting at any distance away from the sun that's possible, right? Any possible distance away from the sun is allowed. You could have a planet here, you could have a planet here, but you could have also had a planet right here in between, orbiting at a different speed. Every single distance is okay. But in an atom, here we go, in an atom, the difference is there's only certain orbits that an electron can be in, okay? I'm going to try to get this to come out as quick as I can. Here we go. Electrons can only orbit in certain places. So an electron can orbit here, and it can orbit here, but it can't orbit here. It's impossible for it to orbit here, just as an example atom. And it might not be able to orbit here either, okay? Now, with that in mind, where do the electrons want to be? Which one of these? They want to go to the center, right? They want to go to the center because they're negative and this is positive, so they want to be attracted in. So which one of these does the electron want to be in? Let's say this was orbit 1, 2, and 3. So just give me a number. Which one do the electrons want to be in? 1, 2, or 3? Yeah, they want to be in 1, right? Because that's the closest to the center, right? So the electrons want to be here. They would love to go all the way in, but they can't. This is the lowest that they can get. And so sometimes we call the lowest orbit the ground state, okay? The ground state. Let me just write it in here. Ground state. Because if you imagined the electrons trying to fall their way in, this bottom level, you can sort of think of that as the ground. When they've gotten that far to the middle, that's as low as they can drop. Just like if you were to fall, the farthest you're going to fall is till you hit the ground, right? Now, let's set this aside for a second, and I'm going to use a metaphor, okay? Let's use a metaphor. Let's imagine I stacked up a table, okay? Let's say I put a table right here. Those are table legs. Here's the table. Okay? There's a table. And let's say on top of that table, let me zoom in a little bit. On top of that table right there, I stacked up another table. And let's say, here we go, So down here is the ground. This is table 1. And this is table 2. Okay? So this is sort of like a metaphor for the orbits of the electrons, okay? You can imagine that the nucleus is way down below the ground, but you can't get any closer to it than the ground, okay? So this down here, this is like the ground state, right? This right here, table 1, is kind of like the next orbit, right? It's the next orbit up from the ground state. And then up here, this table 2 is the next orbit, okay? So it's a bunch of orbits around here. Now, you guys missed out because if you were taking this class in class, like on campus, I actually do stack up 2 tables like this, and then I climb up on the top of the top table, and everybody in the class freaks out because they think I'm going to die. But I'm okay. I'm okay. I choose very stable tables, right? I choose very stable tables, okay? But I'm up here. Now, check this out. Is this right here, is this where gravity wants me to be? Does gravity want me to be up here on this table? If I'm... and I start wobbling around, right? I start wobbling around a little bit. Is this where gravity wants me to be? Yes or no? No. Gravity doesn't want me to be up here, right? Here we go, I can sit here. I can sit here. But if I wobble off a little bit, I could fall. And if I fall, where am I going to end up? I'm going to end up on table 1, right? Here's a quick question, yes or no, could I float in the air right here? Could I float in the air right here? No, I can't, right? Because these tables are kind of like stable points, I can be here, but if I fall, I have to fall all the way down to this table, right? I can't float between them. That's kind of like what I was trying to say up here, where you can have an electron in this top orbit, but if it starts being pulled towards the middle, it's going to end up at this next level. It can't hang out between them. These levels are like tables, right? Now, let me go back to the table. Okay, so here we go. But gravity's not done, right? Because if I wobble off of this table, I can't float here. If I wobble off of this table, I can't float here. So where am I going to end up if I fall off of this table? Whoa. Whoa. Where am I going to end up next? Whoa. On the ground. And yes, in class, I just roll off the table and I just roll onto the ground. Sometimes I kind of smack on my face. It's very exciting. You guys missed out. I'm sorry. So I had to simulate it right here. I fall onto the ground. Now, check it out. When I hit the ground, gravity is still trying to pull me to the center of the planet, but no matter how I roll around, am I going to fall? If I'm rolling around on the ground, am I going to fall anymore? No. So this is kind of like the base level or the ground state. Does that make sense? So this is exactly like the atom, okay? That's exactly like the atom in that this ground state is like the ground, and these are like the upper 2 tables, okay? So the electrons don't want to be up here. They want to fall all the way to the center, just like gravity's trying to pull you to the center of the Earth. And these upper levels are a little bit unstable if you just have 1 electron here. So that means it wants to get pulled to the bottom, okay? Now, we're not quite done with our metaphor, so let me bring the tables back. Here we go. Okay, so let's say I'm on the ground. I'm just laying here. And you want me to be on that first table. Don't overthink this. If I'm just laying here and you want me to be on that first table, what are you going to have to do? What are you going to have to do? If you don't want me to stay down here. Yeah, you're going to have to lift me, right? You're going to have to come over a forklift. Come on, I'm not that big, right? So yeah, you're going to have to lift me, okay? Going to have to lift me up. But here's the important part. Can you come over and give me a weak little low energy lift? Can you come over and just go, eh? If you just come over and just, eh, am I going to get all the way to that table if you just give me a low energy lift? No. You have to give me the exact right amount of energy in your lift. You got to push me the right amount of strength, right? So if you push me with just the right amount of energy, I'll get up to that table and I'll sit on it, right? If you push me with not enough, I'll just fall back down, right? If you push me with not enough, I can't accept that push. I'm going to stay on the ground. But if you push me just right, with just the right amount of energy, you'll get me on the table, okay? But let me ask you a different question. What if you wanted to get me on the second table? What if you wanted to get me all the way up on the top table? How are you going to have to push me now? How much energy are you going to have to use now? More, right? You're going to have to use lots more energy to get me all the way up here, right? So it takes more energy to get to a higher level. But here we go. The important thing here is that this table right here needed one specific energy to get me on it, right? And this other table, that was a different specific amount of energy. If you do anything in between, I'm probably just going to fall back to the ground, right? If you do me anything too little, I'm just going to fall to the ground. So that means, here's the big brain moment that we're going to use on the atom. Each table needs a specific amount of energy to get me up to it. So when we go back to the atom, zoom out a little bit. When we go back to the atom, if the electrons are in the ground state, they're happy. So if you want those electrons to pop up, you have to give them energy. But let's see if we can figure this out. Can I just give the electrons in the ground state a random amount of energy and have it work to pop it to the next level? Can I just give it any random energy? Yes or no? No. Just like with the table metaphor, if I want to pop it to the next table, or in this case level, I have to give it just the right amount of energy. And if I wanted it to pop to the next level, it would need a different amount of energy, okay? And a typical atom could have hundreds of different levels, and each one of them has a special, perfect amount of energy it will take to pop it up. But, here we go. Atoms are microscopic, right? Atoms are microscopic. So how can we give them energy? What's one way? Here we go. Let's see if we can figure this out. There's a reason this is in this chapter. What's a way that I could send energy into these electrons? What's a way? What can I use to send energy into these atoms? And the clue again is there's a reason it's in this chapter. It's light. Good job. Perfect. Remember, light carries energy. So if I send light into this atom, I could pop those electrons out. But, here we go, if that atom will only accept certain energies, then that means most light, when you shine it on it, will do nothing. But if the light you shine on it is the perfect amount of energy, it will absorb, the electron will absorb that light and pop up. Does that make sense? And here we go. Here's the big brain moment. Here's the big brain moment. And somebody's actually already mentioned this. If we can only accept certain energies, then that means that this atom can only accept certain wavelengths. Remember, we said last time, or the last couple of times, that certain energies were certain wavelengths and certain frequencies. That means that if we look at this atom, because it's one particular energy to pop it up to this level, then that means it's one specific wavelength to pop it up to this level. And if you wanted to pop it to the next level, that's a different wavelength. So basically, the different wavelengths of light are the different energies that pop this atom up. Okay, so that means that this atom has only certain wavelengths that it likes. We're almost done with this. This atom has only certain wavelengths that it likes. And every element has a different pattern of wavelengths that it likes, okay? Because every element has different allowed levels. Every element is going to have a different pattern of wavelengths that it will absorb. Yeah, they're picky. That's correct. I kind of call this a fingerprint. Every single element has a certain set of wavelengths that it likes, okay? So basically, you can identify what elements something is made out of by which wavelengths it absorbs, okay?